We are Andrea Osorio and Oscar Alexis Omaña Rogerio, and we're going to present Module 4, Network Access. In order to connect to a network, there are wireless and wired connection. The wireless connection uses no cable, and it must have a wireless access point called WAP where the devices connect. The wired connection is through a cable connected to a switch. The performance of the physical connections differs depending on the type. The downside of using wireless is that the signal weakens when the access point is far, and also the more devices are connected, the slower the performance, because they share the access point. The downside of using a wired connection is that it has its limits in movement, but on the contrary to the wireless connection, each device has its own channel through the Ethernet cable. In order to prevent the weakening of the signal in the wireless connection, we can have a range extender that helps us make the range of the signal wider and it reaches other places. The OSI model divides the data network in layers. The importance of the OSI physical layer is to transport the bits that make up a data link frame across the network media. It receives the complete frame from the data link layer and it encodes it as a signal which are transmitted to the local media. The process of doing this is the user data is separated by the transport layer, packed by the network layer, and encapsulated frames by the data link layer. The physical layer encodes the frames and creates electrical, optical, or radio wave, depending on the case, signals that represent the bits of each frame. Each time, 3 signals are sent, as we can observe on the image. The destination node physical layer retrieves these signals sent and restores them to the bit representation, then passes them to the data link layer to complete a frame. It exists 3 different types of network media: the copper cable that works via electric pulses, the fiber optic cable that works via patterns of light pulses, and the wireless network that works through microwave and radio wave transmissions. The protocols and operations of the upper OSI layers are performed in software. The physical layer consists in electronic circuitry, media, and connectors. There are many different organizations and companies that establish and maintain physical layer standards, for example, ISO, EAI, TIA, ITU/T, ANSI, and IEEE, among others. The physical layer standards have 3 functional areas: the physical components. These are the electronic hardware devices, media, and other connections that carry and transmit signals in bits, for example, NICs, which are network interface cards that have the function to connect to a device to the network. There are different types of NICs like Ethernet for wired and WLAN for wireless. Also, cable materials, interfaces and connectors, UTP and coaxial ports. Then there's encoding, that is a method to convert data bits into code pattern. This pattern can be recognized by the sender and the receiver in zeros and ones. 2 examples of common methods are the Manchester encoding, when a 0 is represented by a high to low voltage and the 1s are represented from low to high voltage. There's also the non-return to 0 method, when a 0 is represented by a level of voltage and the 1 another level of voltage on the medium. Then there's the signaling. This is how the 1s and 0s are represented in the signal with pulses. There are two ways of doing this. In an asynchronous way, where data signals are transmitted without an associated clock signal, the time spacing between data characters may be arbitrary, so the frames require start and stop indicators. Synchronous, these data are transmitted with a clock signal, and the times between data characters are determined and always the same. The way to transmit the signals can be through frequency modulation (FM), amplitude modulation (AM), and pulse-coded modulation (PCM). Also, it affects the changes in the magnetic field and the intensity of the electromagnetic field. Physical media transfers bits in different speeds. This is called data transfer, and it is in terms of bandwidth and throughput. The bandwidth is the capacity of the medium to carry data. If it is digital, it measures the data quantity that flows from one place to another in a determined time. It is measured in kilobits per second or megabits per second. This bandwidth is determined by several factors, such as the properties of physical media, the technologies used for signaling and detecting network signals, and throughput measures the transfer of bits across the media in a given time. It is determined by several factors, such as the amount of traffic, the type of traffic, the latency, which is the time data transfers and delays of traveling time, the total time plus the delays of the traveling time created by a number of network devices encountered between source and destination. This can be measured by speed test, and this is what a speed test such as speedtest.com measures. In copper cleaving, copper is inexpensive, easy to install, and has low resistance to electrical current, but it is limited with distance and usually possesses signal interferences. The data is transmitted in copper with electric pulses, so the interferences that have downsides on the copper are electromagnetic interferences or radio frequency interferences signals that can distort or corrupt data through the copper wire. This can be prevented by wrapping the cable with metal and ground connections. There's also the crosstalk interferences. This is caused by electric or magnetic fields. It distorts the signal. This can be prevented by having the opposite circuits wire pairs being twisted together. As we can see in the image, there's the pure digital signal, the interference signal, and then the combines. And as we can see in what the computer reads, where it should be a 0, it's a 1. So that's what caused the interferences to not put the signal as it should be. There are three main types of copper media. UTP, that is the unshielded twisted pair, STP, shielded twisted pair cable, and the coaxial cable. Here is the structure of a UTP cable. There's an outer jacket that is made from plastic that prevents the wire from physical damage. Also the twisted pair that protects the signal from interferences, The more twisted the pair is, the less probability it has to be interfered, and the color-coded plastic insulation, which differentiates and identifies the different pairs of cables. Here is the image of the STP cable, and it has also the jacket, but inside, instead of having only the twisted pairs, it has two shields, the braided or foil shield and the foil shields. This is in order to protect it from noise and crossover communications. And this is the coaxial cable. The coaxial cable has the outer jacket, then a braided copper shielding and the plastic insulation. There are three types of coaxial connections, and it's the B and C, the N-type and the F-type. Copper wires are very susceptible to having electronic hazards, so we can prevent this from happening. In order to do this, the separation of data and electrical power cabling must be complied with safety codes. Cables must be connected correctly. Also, installation must be inspected for damage. Equipment must be grounded correctly. There are different categories of UTP cable. There's the category 3, the category 5 and 5E cable, and the category 6. The bigger the number in the category are, the more functionalities it has, and the better the quality of the cable. These are the types of categories according to the IEEE, the Institute of Electrical and Electronics Engineers. There are two types of standards that are important in order to differentiate a straight through from a crossover cable. There's the TIA 568A, or also called as Type A, or the TIA 568B, called T-Type B. The Ethernet straight-through cables are the ones that both ends with Type A or both ends with Type B, and it is used to connect a network host to a network device such as a switch hub. The Ethernet crossover has one end with Type A and the other with Type B. That's why it's called crossover. It is used to connect two network hosts, also to connect two network intermediary devices, switch to switch or router to router. And there's also the rollover cable, that it has the standard not by the IEEE but by Cisco. And it is used to connect a workstation serial port to a router console port using an adapter. In order to test the functionality of the cable tester, of the cable, UTP cable, we can use a UTP cable tester, which determines if a cable is functional. This tester see the wire map, the cable length, if there is crosstalk and signal loss due to attenuation, and determines if the cable is functional. Now we're going to talk about a fiber optic cabling. This kind of cabling have the advantages of transmission of data in larger distances, higher bandwidths, minimal loss of signal, and immune to electromagnetic interference or radio frequency interferences. It is very thin and flexible. The bits are encoded as light pulses generated by lasers or LEDs. It is composed of two kinds of glass and an outer shield called core, cladding, and jacket. The core is made of pure glass, and it is where the light is carried. The cladding is made from different chemicals and it surrounds the core. It acts as a mirror and reflects the light back into the core of the fiber. Then there's the buffer that helps to shield the core and the cladding, preventing it from any damage. It has an strengthening material that surrounds the buffer, preventing the cable from being stretched when it is pulled. And there's also the jacket that is made from PVC and protects both the core and the cladding from scratches and moisture. Fiber optic cables are classified in two types. The single mode fiber, which is when the core is very small, but uses expensive laser technology. It is used for long distance situations. There is also the multi-mode fiber, that has a larger core and it doesn't use laser but LED emitters. And it has multiple paths of light, as we can observe in the image. It is used mostly for lamps and it has a bandwidth up to 10 gigabits per second and wavelength up to 550 meters. There are different types of optic connectors. The straight tip that is used with multi-mode fiber, the subscriber connector that it is a square connector or a standard connection. Then it is used for LAN and WAN connectors. It may be used in both single mode and multi-mode fiber. And there is the lucent connector. It is a very little and local connector. It is used with single mode, but it also supports multi-mode. Also, there are different types of cords to differentiate single mode from multi-mode. When the fiber's cable don't work, it's due to a misalignment and gap. That is when the media does not touch at the connection, or end finish, that is when media ends are well not polished or with dirt. To determine this, we can use an optical time domain reflectometer. Now we're looking to a table with the differences between the UTP cabling and the fiber optic cable. As we can see, the bandwidth supported, the fiber optic cabling has higher bandwidth than the UTP cabling. Also, the distance is a lot higher because in UTP cabling it only goes up to 100 meters and with fiber optic cabling to 100,000 meters. Fiber optic has complete immunity to electromagnetic interferences and radio frequency interferences, and it has immunity to electrical hazards, contrary of UTP cable, which has a lot of probability to these interferences and hazards to happen. The media and connector costs, the installation skills required, and the safety precautions are really high in fiber optic cabling. It is a lot more easier to install copper cabling. It is also less expensive. Now we're going to talk about wireless media. Wireless media works with electromagnetic signals representing binary digits of data using radio or microwave frequencies. The main issues with this type of media is the coverage area because the environments affect the performance of the network. Also, interferences is more probable to happen because the other devices such as microwave ovens, cordless phones, and many others might affect it. Security is also an issue in wireless communication because there isn't a protection in the transmission. This provokes to be a major concern of attention to the security of the network. The common data communication standards in wireless media are IEEE 802.11, IEEE 802.15, and IEEE 802.16. These are different because the .11 is commonly referred as Wi-Fi, and it has a lot of variations that have evolved through time that we're going to talk about later. The .15 supports speeds up to 3 megabits per second and provide device pairing over distances from 1 to up to 100 meters. And the .16 standard provides speed up to 1 gigabit per second. It uses a point-to-multipoint topology to provide wireless broadband access. Here we have the different evolutions of the .11 standard, and as we can see, it has different range of maximum speed, frequency, and backward compatibility. The Type A has a maximum speed of 54 megabits per second, a frequency of 5 gigahertz, and is not backward compatible. This is the first one of the standards of Type A. Then if we see the Type AD, it has up to 7 gigabits per second, and that's 7,000 megabits per second of maximum speed. It has 2.4 gigahertz, 5 gigahertz, and 60 gigahertz of frequency, and it is backward compatible to all the previously versions.
Okay, now we will see the data link layer protocols. The TCP/IP network access layer is the equivalent of the layer 1 and 2 in OSI. The data link layer is responsible for the exchange of frames between nodes over a physical network media. It allows the upper layers to access the media and controls how data is placed and received on the media. The data link layer performs two basic services. It accepts layer 3 packets and packages them into data units called frames, and it controls media access control and performs error detection. The data link layer is actually divided into two sublayers. The first one is the logical link control, LLC, which defines the software processes that provide services to the network layer protocols. It places information in the frame that identifies which network layer protocol is being used for the frame. The second is the media access control, which defines the media access processes performed by the hardware. It provides data link layer addressing and delimiting of data according to the physical signaling requirements of the medium and the type of data link layer protocol in use. Layer 2 protocols specify the encapsulation of a packet into a frame and the techniques for getting the encapsulated packet on and off each medium. This technique is called the media access control method. As the packet travels from source host to destination host, the packet is most likely to go through different physical networks, as shown in the figure. Those physical networks can be copper wires, optical fibers, and wireless signals. The packets do not have a way to directly access these different media. It is a role of the OSI data link layer to prepare network layer packets for transmission and to control access to the physical media. The media access control methods described by the data link layer protocols define the process by which network devices can access the network media and transmit frames in diverse network environments. Different media access control methods may be required during the course of a single communication. Each network environment that packets encounter as they travel from local host to remote host can have different characteristics. Router interfaces encapsulate the packet into the appropriate frame, and a suitable media access control method is used to access each link. In any given exchange of network layer packets, there may be numerous data link layer and media transitions. At each hop along the path, a router accepts a frame from a medium, de-encapsulates the frame, re-encapsulates the packet into a new frame, and finally forwards the new frame appropriate to the medium of that segment of the physical network. The data link layer prepares a packet for transport across the local media by encapsulating it with a header and a trailer to create a frame. The description of a frame is a key element of each data link layer protocol. Those protocols require control information to enable the protocols to function. Control information typically answers which nodes are in communication with each other, when does the communication between individual nodes begin and when does it end, which errors occurred while the nodes communicated, and which nodes will communicate next. Unlike other PDUs that have been discussed in this course, the data link layer frame includes a header, a data, and a trailer. Later we will see what are those parts. When data travels on the media, it is converted into a stream of bits, or ones and zeros. But if a node is receiving long streams of bits, how does it determine where a frame starts and stops, or which bits represent the address? Framing breaks the stream into decipherable groupings, with control information inserted in the header and trailer as values in different fields. This format gives the physical signals a structure that can be received by nodes and decoded into packets at the destination. The generic frame field types are shown in the figure, but not all protocols include all of these fields. The standards for a specific data link protocol define the actual frame format. Next, unlike the protocols of the upper layers of the TCP/IP suite, data link layer protocols are generally not defined by the RFCs, which are the request for comments. And although the Internet Engineering Task Force maintains the functional protocols and services for the TCP/IP protocol suite in the upper layers, the Internet Engineering Task Force does not define the functions and operation of the model's network access layer. Some of these standards integrate layer 1 and 2 services. Engineering organizations that define open standards and protocols that apply to the data link layer include the Institute of Electrical and Electronics Engineers, the International Telecommunication Union, the International Organization for Standardization, and the American National Standards Institute. Here in the table there are some of their more important standards. Now let's see the media access control. Regulating the placement of data frames onto the media is controlled by the media access control sublayer. Media access control can be equivalent to the traffic rules that regulate the entrance of motor vehicles onto a roadway. For example, let's imagine the traffic here can enter in several ways. It can wait for the traffic lights or it can enter by waiting its turn in the stop sign, or by simply one road merging to the other road. So the driver follows a different set of rules for each type of entrance. There are different ways to regulate placing frames onto the media. The protocols of the data link layer define the rules for access to different media. Some media access controls methods use highly controlled processes to ensure that frames are safely placed on the media. These methods are defined by sophisticated protocols, which require mechanisms that introduce overhead onto the network. The actual media access control method used depends on the topology, that means how the connection between nodes appears to the data link layer, and the media sharing, that is how the nodes share the media. Physical topology. The topology of a network is the arrangement or relationship of the network devices and the interconnections between them. LAN and WAN topologies can be viewed in two ways. The first one is the physical topology, which is on screen right now, and it refers to the physical connections that identifies how end devices and infrastructure devices such as routers, switches, and wireless access points are interconnected. Now, the logical topology, it refers to the way a network transfers frames from one node to the next. This arrangement consists of virtual connections between the nodes of a network. These logical signal paths are defined by data link layer protocols. The data link layer sees the logical topology of a network when controlling data access to the media. It is the logical topology that influences the type of network framing and media access control use. Now, let's see the WAN topologies. WANs are commonly interconnected using the following physical topologies. The point-to-point topology, which is the simplest topology, which consists of a permanent link between two endpoints. For this reason, this is a very popular WAN topology. Next is the hub and spoke topology. It's like one version, a WAN version of the star topology, in which a central site interconnects branch sites using point-to-point links. And finally, the mesh. This topology provides high availability, but requires that every end system be interconnected to every other system. Therefore, the administrative and physical costs can be significant. Each link is essentially a point-to-point link to the other node. Now, the physical point-to-point topologies directly connect two nodes as shown in the figure. In this arrangement, two nodes do not have to share the media with other hosts. Additionally, a node does not have to make any determination about whether an incoming frame is destined for it or another node. Therefore, the logical data link protocols can be very simple, as all frames on the media can only travel to or from two nodes. The frames are placed on the media by the node at one end and taken off by the media by the node at the end of the point-to-point circuit. Now, the end nodes communicating in a point-to-point network can be physically connected via a number of intermediate devices. However, the use of physical devices in the network does not affect the logical topology, as we can see right now. As shown on screen, The source and destination node may be indirectly connected to each other over some geographical distance. In some cases, the logical connection between nodes forms what is called a virtual circuit. A virtual circuit is a logical connection created within a network between two network devices. The two nodes on either end of the virtual circuit exchange the frames with each other. This occurs even if the frames are directed through intermediary devices. Virtual circuits are important logical communication constructs used by Layer 2 technologies. The media access method used by the data link protocol is determined by the logical point-to-point topology, not the physical topology. This means that the logical point-to-point connection between two nodes may not necessarily be between two physical nodes at each end of a physical link, of a single physical link. Now, here we have a point-to-point connection. In point-to-point networks, data can flow in one of two ways. The first one is the half-duplex communication. In this one, both devices can both transmit and receive on the media, but they cannot do it simultaneously. So here we can see either it receives or it sends, but they cannot do it simultaneously. And here we have the full duplex communication, in which both devices can transmit and receive on the media at the same time. The data link layer assumes that the media is available for transmission for both nodes at any time. Therefore, there is no media arbitration necessary in the data link layer. Now let's see the LAN topologies. We have here the star topology. The star consists on n devices that are connected to a central intermediate device. Nowadays, star topologies use switches. The star topology is the most common physical LAN topology, primarily because it is easy to install and very scalable, meaning it's easy to add and remove n devices, and easy to troubleshoot. We have here the extended star topology. As the name says, it's a extended star topology. Central intermediate devices interconnect other star topologies. In a hybrid topology, the star networks may interconnect using a bus topology, which is right here, the bus topology. On the bus topology, all n systems are chained to each other and terminated in some form on each end. Infrastructure devices such as switches are not required to interconnect the end devices. And finally, the ring topology. In here, the end systems are connected to their respective neighbor, forming a ring. Unlike the bus topology, the ring does not need to be terminated. The logical topology of a network is closely related to the mechanism used to manage network access. Access methods provide the procedures to manage network access so that all stations have access. When several entities share the same media, some mechanism must be in place to control access. Access methods are applied to the networks to regulate the media access. Some network topologies share a common medium with multiple nodes. At any one time, there may be a number of devices attempting to send and receive data using the network media. There are rules that govern how these devices share the media. There are two basic media access control methods for shared media. The contention-based access, in which all nodes compete for the use of the medium but have a plan if there are collisions, what is on the screen right now is a contention-based access, and then we have the controlled access, in which each node has its own time to use the medium. Now, a logical multi-access topology enables a number of nodes to communicate by using the same shared media. Data from only one node can be placed on the medium at any one time. Every node sees all the frames that are on the medium, but only the node to which the frame is addressed processes the contents of the frame. So we can see here that the computer A needs to send something to the computer E. So as I previously said, every node sees all the frames that are on the medium. So the nodes is A, C, B, and D, but they realize that the frame is not for them, so they just delete it, and then it continues its way to the computer E. Having many nodes share access to the medium requires a data link media access to control method. No. Having many nodes share access to a medium requires a data link media access control method to regulate the transmission of data and thereby reduce collisions between different signals. In here, when another device wants to transmit a frame, it has to wait for the transmission of the previous one to end. So when the previous transmission ends, now the other end device can send its own frame. Now, when using the control access method, network devices take turns in sequence to access the medium. If an end device does not need to access the medium, then the opportunity passes to the next end device. This process is facilitated by the use of a token. An end device acquires the token and places a frame on the media. No other device can do so until the frame has arrived and been processed at the destination, releasing the token. This method is also known as scheduled access or deterministic. Although control access is well ordered and provides predictable throughput, deterministic methods can be inefficient because a device has to wait for its turn before it can use the medium. In a logical ring topology, each node in turn receives a frame. If the frame is not addressed to the node passes the frame to the next node. This allows the ring to use a controlled media access control technique called token passing. Nodes in a logical ring topology remove the frame from the ring, examine the address, and send it on if it's not addressed to that node. In a ring, all nodes around the ring examine the frame. As we can see here, the frame has passed through these nodes, and then the frame reaches the node it was addressed. Now, each frame type has three basic parts: the header, the data, and the trailer. The data link layer protocol describes the features required for the transport of packets across different media. These features of the protocol are integrated into the encapsulation of the frame. When the frame arrives at its destination and the data link protocol takes the frame of the media, the farming information is read and discarded. As in shown on the screen right now, a fragile environment requires more control. However, a protected environment requires fewer control. The frame header contains the control information specified by the data link layer protocol for the specific logical topology and media use. Frame control information is unique to each type of protocol. It is used by the Layer 2 protocol to provide features demanded by the communicating environment. So we have here a start frame field that indicates the beginning of the frame, the address or source and destination address fields, which indicate the source and destination, nodes on the media, and the type field that indicates the upper layer service contained in the frame. However, different data link layer protocols may use different fields from those mentioned. And finally, the frame trailer. Data link layer protocols add a trailer to the end of each frame. The trailer is used to determine if the frame arrived without error. This process is called error detection and is accomplished by placing a logical or mathematical summary of the bits that comprise the frame in the trailer. Error detection is added to the data link layer because the signals on the media could be subject to interference, distortion, or loss that could substantially change the bit values that those signals represent. Finally, in a TCP/IP network, all OSI Layer 2 protocols work with the IP at OSI Layer 3. However, the actual Layer 2 protocol used depends on the logical topology of the network and the implementation of the physical layer. Given the wide range of physical media used across the range of topologies in networking, there are correspondingly high number of Layer 2 protocols in use, as you can see right now on screen. The protocol is changing depending on the logical topology of the network. And that will be all for the module 4.